Welcome to the Ex Terra Podcast. The Ex Terra mission is to explore and discuss the business of space and its effect on the national and global economy, as well as life on Earth. How does what happens in space affect your life every day? That's what we're exploring on the Ex Terra website, as well as on this podcast. Our guest on this edition of the Ex Terra Podcast is Rick Ward, founder of OrbitsEdge. Rick, thanks for joining us.
Hello, Tom. It's nice to be here.
Let's start with the basics. Rick, what is OrbitsEdge and what does your company do?
So OrbitsEdge is a company dedicated to putting high-powered compute in space, in low Earth orbit, and then moving beyond there.
So give me a definition of edge computing.
Okay, so if you're familiar with cloud computing, that is doing your processing on somebody else's computer. If you're in an edge environment, such as out in the desert or out in the jungle or out in the tundra, you don't have anybody else's computer nearby. So you have to do it on your own computer. And that's generally done for questions of latency, or the distances are so great that it's just really inconvenient to transmit large sums of data there and back.
Then what are the benefits of bringing high performance computing to space?
Okay, it's basically the same thing. In one sense, it's a totally new thing because nobody's ever done high-powered compute in space. In another sense, it's the same thing that people have already done 1,000 times. It is bringing edge compute to a new location with all the same reasons: latency, backhaul, bandwidth constraints, time constraints, all the same reasons that apply to edge compute cases here on Earth apply to edge compute in space.
How do you go about that then? What's the process of getting data up to space, crunching it, and getting it back down to where it's needed?
So what we're actually looking at is working with data that originates in space, such as Earth observation data. That is actually our biggest use case that is currently existent today. So that's about taking data that originates or collates in space, doing some initial compute operations, and then packaging that and getting it down to Earth in a more efficient manner than what's currently possible.
How do the satellites talk to one another? How do you get that data?
Satellites do have phased array communications that can be used to talk to either ground or to another satellite. One of the advantages when a satellite talks to another satellite is you have orders of magnitude lower power requirements, because in order for a satellite to talk to the ground, it has to cut through the entire atmosphere. In order for it to talk from satellite to satellite, it doesn't have to do that.
I've heard a lot about advances in laser communications by satellite. Is that going to make things a lot easier for your company?
There's a lot of companies that are currently working on laser communication modules, and that's going to be a fantastic boon, because it has much higher bandwidth, obviously, and the FCC requirements are basically nil on that. It's not hard to get bandwidth allocation, which is a major component of the difficulties in doing RF communications. So it's going to enhance the ability to put data on the ground. It has its cons also. For instance, laser only works, currently laser only works in basically desert environments. So you can't do it in a place with high humidity. The atmospheric attenuation is too much, but that's presumably something that's going to be improved over time. But the issue still remains where the amount of data created is more than what can be backhauled to Earth. And that problem is only growing. It's going to be an insurmountable thing. So there's still going to be a place for edge compute.
Do you see a time when there will be operators on the ground who are uplinking to satellites to your edge computing, your processors to use that system to forget a broader distribution? Is that a case that you look at, or is it going to be strictly from Earth observation satellites to bring it back to scientists on Earth?
Yeah, that's actually one of the considerations. We are an edge solution,
Mm-hmm.
about 200 kilometers away from you is the way we put it,
Mm-hmm.
because we're over your head. So if you're in a disaster recovery, if you're in some sort of you need infrastructure in a place where none exists,
Mm-hmm.
then we could potentially be your best solution for that.
Is radiation a problem for high performance computing? Space is a high radiation environment. What kind of unique challenges are there in that?
Yes, there are two big challenges to doing high-powered compute in space, and radiation is one of them. There's a couple of things that can happen to computers in space. You can get random bit flips, which is where a, a particle of radiation strikes your storage and it turns a 1 into a 0. You would think that wouldn't be a big deal, but it actually is a big deal. Because it means that you're putting garbage data into something and then you're getting garbage data out of it. It can be significant. So there's ways to combat that. Generally, it's redundancy, it's triplication. So you have 3 copies of the same data, and whenever you see a difference between, say, any difference, you compare A and B, and C is different. Well, you're going to make the assumption that A and B didn't both change in the same place, so C has the error. So that's something that's been done for a long time. That's part of the software solution that we have. We also do some radiation shielding. It is against certain spectrums of the radiation environment, but you can't do all of it because that is prohibitive in terms of mass and physics and cost. Mm-hmm. So we're going to shield what we can and work with software to get around the rest. It's radiation mitigation.
It sounds like you're talking about what an IT person on Earth would call a RAID array, that you have multiple disks with the same data for redundancy.
Right, it's exactly that.
Now, what about power and thermal issues? That always seems to be an issue for space technologies across the board. Is computing in space any different?
That is the other half of the problem.
Okay.
So computers are basically almost 100% efficient heaters that happen to create numbers as a side hobby. However efficient it is, you put a watt of power into a computer, you're getting a watt of heat out of it. So what we're working on is a power management solution. Also, our computers are much thirstier than normal computers. We're talking about micro data servers. However efficient they are, they still perform a lot of computation, so they take a lot of power. And we're looking at about a kilowatt hour power budget. So that is not insignificant. That's a lot of that's a lot of solar panels, it's a lot of batteries, and it's a lot of heat on the back end. So our solution handles thermal management. It carries the heat away from the components, and we dump it into the coldness of space as opposed to the hotness of space.
Do you have an issue on the thermal side of it where if one side of the satellite is more towards the sun and the other is away, does that create a real thermal delta that you have to deal with?
It's a big fat delta, yes. The portion of a spacecraft that has light shining on it will be about the temperature of an oven on clean cycle, and the portion right next to it, like a millimeter away in shadow, will be the temperature of, let's say, liquid oxygen.
Okay.
So that is a not in, it's a significant delta. The best solution we've come up with for that is to use the solar panels, because we have a lot of solar panels,
Mm-hmm.
as a parasol to enable the radiation shielding to hide behind that. So we only have to deal with the entire computer is in the cold portion.
Mm-hmm.
We can use the heat from the computer itself to keep it warm enough, and then we can regulate we have two means of regulation. We can regulate through through the read output, so through the computation speed.
So how specialized and unique are those technologies that you need to bring this high-powered computing to space?
Well, nobody's done it before. So nobody's done it before for two different reasons. Launch costs are very high. The computer components have not been able to generate a cost-effective amount of work. So I was talking before about the power use and efficiency. Moore's law says that computers get faster over time.
Mm-hmm.
Not the same computer, but the new ones. So the amount of work you could get out of a computer, say 10 years ago, was not so much that you could justify the mass and the power requirements.
Right.
So computers are getting better, solar panels are getting better, batteries are getting better, while launch cost is coming down. So you kind of have all of those things. Those charts are intersecting at the right points to make it a cost-effective proposition to put compute in space today.
That's like that old adage that we all have more computing power in our phones right now than NASA used to put men on the moon.
Absolutely. And one of the most popular processors today is approximately equal to the original iPhone in computation. It is the RAD 750. It's a processor from the PowerPC 750, if you are familiar with the mid-90s. And it's still in production today, and it went off on the Mars Perseverance rover. So it's the computation landscape out there is not cutting edge.
Talk about the cost effectiveness for edge computing in most space applications. Why would someone want to come and use your service as opposed to just downloading the data on their own and doing it terrestrially?
Right. So as is, a satellite is a dumb creature. It does what it's told, and it doesn't know what it's doing. It has the capacity to take a lot of pictures, orders of magnitude more pictures than it will ever have the ability to get down to Earth. Okay. It could take thousands of pictures on a pass, but it only has the bandwidth, small fraction of those pictures down to Earth. So therefore, it's only ordered to take specific pictures at specific points that human operators are interested in. So as I'm interested in a picture of grid point A. Okay. So I tell the computer, the satellite, to take a picture of grid point A, and I'm also interested in B, C, D, E. I take all of those pictures and tell the satellite to send them down A through F, send them down on the next conjunction with a ground station. And it sends those down, but it doesn't have the ability to get receipt of acknowledgement of receipt of transmission. So it dumps those, and now it takes G through L or so, and then it sends those down. And if you didn't get one, you just didn't get it. Okay. Also, if the picture happened to show nothing but clouds, you get that, and that's too bad. If it showed Or let's go into a slightly more advanced case. Nothing has changed. Literally nothing has changed. You're taking a picture of the middle of the desert. You're taking a picture of a factory. Most of that image is not going to be significantly different from one pass to the next.
Right.
You might be interested in things like what kind of activity is going on there. What's the parking lot look like? What are they doing construction today? In that scenario, you can do what's called change analysis, where you look at the picture from last week or last month or last year or whatever, and compare it to the picture today. And you say, well, most of that is the same. There are some differences here, here, and here. And you cut out those different images, those different portions of the image, and you send down only those. There might be other cases where what you're really interested in is how many people are out shopping right now? How many people are going to Walmart? How many people are going to all these places? Does AMC have a chance to survival because people are going to their movies right now?
Right.
In that scenario, you don't even want the image. You just want a number. You just want a spreadsheet. And you can do that computationally, turn that image into a spreadsheet, and you can download 1,000 spreadsheets that describe how many cars are in parking lots for the cost of one image. So you can really generate a lot more actionable intelligence with compute, orders of magnitude, many orders of magnitude, more actual information than you can just by getting raw images. Because at the end of the day, it's not going to be a guy looks at that picture on the ground and says 1 car, 2 car, 3 car, 4 car. You're going to feed it through another AI here, and that's going to generate you the spreadsheet. You'll never see the actual raw images because you don't care about seeing 100 pictures of parking lots.
Right.
So that's what it's about.
You're listening to the Ex Terra Podcast. I'm Tom Patton, and we're talking with Rick Ward, the founder of space edge computing company OrbitsEdge. Rick, on your website, you talk about the orbital data bottleneck. What is that, and how do you address it?
So the data bottleneck is basically saying that you don't have the ability to transmit as much stuff as you'd like to. So why is that? Bandwidth is a precious commodity in the space industry. They have auctions for it. It's allocated. It a year or two of work and fees and lots of stuff to get an allocation for a thin portion of the bandwidth. From there, you have ground stations. You are not continuously connected to the ground. You don't have a constant data link. What happens is you pass over a ground station, which is usually going to be on a mountainside or mountaintop rather, or out in the middle of the desert or something like that. A place that is sited so that the weather usually doesn't interfere with it. And as you're over that ground station, you have up to several minutes of transmit time. Also, transmitting takes a lot of power. You have to cut through the whole atmosphere. So the battery capabilities, the power capabilities that your satellite has on board are going to be an inherent limiting factor. I can't just buy subscriptions to 5 more ground stations and get five more ground stations worth of data down. That has to be a function of the amount of solar panels and batteries that I have on board. And those things degrade over time. So there comes a point where I only have the power budget to send down fewer images than I could send down on the same satellite a year prior. So that's the real thing. It's a constraint-based thing. It's not a continuous pipeline as we're used to here on the ground.
So then how do you address that issue?
So we address that by taking the data off of the satellite ourselves, which, well, they send it to us.
Mhm.
As I mentioned before, it takes a lot less power to send information from sat to sat than it does sat to ground.
Mhm.
And we can do sifting and processing and compression as well as encryption that gives us the ability to have orders of magnitude. I love that phrase, apparently. More data density of quality data, of high quality data than what is possible with a straight pipe.
You mentioned also a while back about the advances in computing and how quickly those things change. When you look at what you're intending to put into space soon and where you might want to be in 5 to 10 years, what kind of I want to say refresh rate do you have on the hardware that you're planning to put into space?
So the way our architecture is planned, we're building the box.
Mm-hmm.
We're not building the compute. We're not doing outlandish modifications to the compute. We're just taking the compute, putting it in the box, and going with that. By doing so, that gives us the opportunity to refresh every year. When new stuff comes out, we get a hold of it, ideally early on, and we check it out, make sure that it's going to fit in the box properly. The box is kind of scalable,
Mm-hmm.
so we can go up or down a bit. We can make modifications internal as needed. And we plan to be flying the next year's stuff within a few months of within a few months of receiving it.
Are you talking about CubeSats, small sats, full-size satellites? What kind of birds are you flying?
So what we're looking at is from small sats up. We're looking at something approximately the size of a mini fridge,
Okay.
up to the size of a stand-up refrigerator in a residential, up to the size of let's say an SUV,
Okay.
ultimately. But our original missions are intended to be more in the mini fridge to stand-up fridge size.
Your company's publicly stated you're working with Hewlett Packard Enterprises to create a data center in space. How are they to work with, and what kind of special computing technologies are they bringing to the table?
They are fantastic to work with. They have an inherently security-based architecture.
Mm-hmm.
They have high reliability, and they've actually provided us with some of their HPE Edgeline EL8000 computers that are highly configurable. They have a blade arrangement. The ones we currently have are pushing 4 Tesla T4 GPUs. So that's a lot of computation for AI right there. HPE also has the benefit of being the only company who has currently flown high-powered computers in space.
Mm-hmm.
So they currently have Spaceborne Computer 2, which is, as you might have guessed, the successor to Spaceborne Computer 1. That one flew. It was in space for over 600 days. It was running for about a year and a half. The rest of that time, it was packed up in storage, either before or after launch. The new one was carried up on the Cygnus launch from Wallops Island on February 14th, I think it was.
Mm-hmm.
I actually went up there, met with the principal investigator. We had good conversations. We saw the launch together, and we talked about a lot of the stuff that they're doing on the mission. HPE learned a lot of lessons from Spaceborne 1. We had conversations back and forth with them in the aftermath of that and in their run up to Spaceborne 2. And we learned a lot from them, and we also passed on what we had picked up in our research back to them to make Spaceborne 2 a better success than it otherwise would have been, I hope.
We hear a lot about computer hacking. What kind of security issues are there particular security challenges in a space-based computing system as opposed to something terrestrial?
Well, it's in space and nobody can touch it, so it's safe, right?
That
Yeah.
doesn't mean they can't hack it.
No, it does not. No, it does not. A lot of people seem to think proximity matters more than it does. So for that, I mentioned that. So your computers are only as generally it's the user that's the problem.
Right.
It's things like dumb passwords. It's things like not locking things up that you should have. We have, by using cutting edge commercial off the shelf hardware, we're enabled to operate current software. So a lot of these satellites that exist today, they either don't have encryption or they have pretty rudimentary encryption, to the point where you assume that the encryption is going to delay reassembly of data by hours, not indefinitely. And our hardware stack enables robust security measures to be taken. So we're actually planning on charging by how much computation is done, which is not normally done, but hey, we're the only ones with the asset, so therefore, and that's the whole point of it. So if you want to do encryption, that's a high level encryption, even is around, say, 3 to 5% more computation than you would put into it without encryption. So that seems like a fairly easy add-on to choose. And yeah, it's really a matter of modern hardware lets you use modern software, and that enables modern security.
NASA selected OrbitsEdge to participate as a finalist in the 2020 NASA ITech Cycle 2 Forum. Tell me a little bit about that.
Yeah, that was a great forum. There were a lot of serious competitors out there, a lot of really good ideas. There was a lot of back and forth with NASA about we like the way you're saying this, we like the way you're explaining this, and maybe you could do a better job with this or that. Or it was a really important growing opportunity. There was a lot of learning done in a relatively short period of time. So that was a tremendous opportunity to be part of, and the whole team did a really good job in getting through that.
I'm going to close, Rick, asking you to kind of gaze into your crystal ball a little bit and talk to me about where you see computing in space in a 5-year or a 10-year time horizon.
Oh God. Yeah. So what I've really talked about with Earth imaging is the low-hanging fruit. As you get farther away from the Earth, latency becomes a bigger issue. You get to the moon and you're looking at about a 1.2 second time lag for information to go from Earth to the moon and back, or the opposite trip. And if you're going to do any sort of mining operations, you're going to do a habitat, you're going to do any sort of sustained operation, you really need to do better than that, especially if people are involved. Human safety is involved. So you need local compute. OrbitsEdge is intended to start out in LEO, but we're not planning on staying there. We're planning on going to GEO, cislunar, and beyond. We're planning on going everywhere people go. So that means the moon, Mars. We get out to the main asteroid belt, we want to be there. You go to Jovian and Saturnian moons, you're going to need what we offer. So yeah, that's where I see maybe not 5 to 10 years, but that's where I see things going.
About a year ago, Rick, you were projecting your first launch late this year in 2021. Is that timeline still accurate, and what do you have left to be done?
That timeline is not fully accurate at this point.
Fair enough.
Yeah, the current events that have dominated 2020 have dominated a lot of things. We've done a lot of important work through that time, but not necessarily the work that directly correlates to a launch. That is still ongoing, but that timeline is turned out to be a bit optimistic.
Well, we'll keep an eye on it, Rick, and hopefully when you get that launch going, we'll come back and talk with you again.
Thank you very much. I'm looking forward to that.
We've been talking to Rick Ward, who's the founder of the space edge computing company OrbitsEdge. And that's going to do it for this edition of the Ex Terra Podcast. Find us on the web at xterrajsc.com. And be sure to connect with us on LinkedIn and follow us on Twitter at XTerraJSC. Until next time, I'm Tom Patton. Thanks for listening.